Alright, good morning everybody. Welcome back to Non-Euclidean Geometry. Plan for today is we are going to wrap up our packet on logic and then start a big beefy 14-page packet on instance geometry, which is going to take us through the rest of chapter 2 and will start taking us down the rabbit hole of non-Euclideanness. I've got usual office hours today after class and from 2 to 3 tomorrow morning at 10 and tomorrow afternoon at 1. I posted the other day on Canvas a new homework set, homework 2. Just a few problems and will be due next Wednesday in class. So you have a week to work on it. Also, we are going to have a quiz this Friday over the logic packet. One thing we're going to get into instance geometry in the second half of class today, but the quiz will only cover up to through the logic packet. Any questions or comments before we get started today? Yes, Elaine? Oh, of course. Wow, 6th grade 7. Really, no one's going to help you?
Because 7, 8, 9.
It's because 7, 8, 9. But why did 7 eat 9? Because 7 knows the importance of eating 3 squared meals a day. Okay, so last class we talked about how to write kind of the general idea behind writing mathematical proofs. Looking at the different types of ways you can sort of justify a statement, give a logical flow by definition, by a postulate, by a previously proven result, by some rule of logic. And we also talked about a specific proof technique called proof by contradiction, or reductio ad absurdum, where if you have an implication like this, if hypothesis then conclusion, we discussed how the way we could prove that is by assuming the hypothesis is true and the conclusion is false, and then showing that you somehow arrive at a contradiction. Something impossible ends up happening. So in our case, the theorem you looked at is good old hypothesis of Ponton's. If ABC is a right triangle with AB equals BC equals 1, that AC cannot be written as a quotient of integers. In other words, square root of 2 is irrational. And the general strategy that we used is we assumed the hypothesis is true, meaning we assumed we do have a right triangle where AB and BC have side lengths of 1, and we assumed that the hypotenuse AC has a length that we can write as a quotient of integers, x over y, and then we basically arrived at a contradiction by saying, as part of our assumption, we assume that x over y is a fraction in lowest terms, because if it wasn't in lowest terms, we could just cancel out common factors in the top and bottom until it was in lowest terms. And then we showed that even if we wrote x over y in lowest terms, under this assumption, it would have to be the case that x and y are both even, and thus the fractions, it can never be put in lowest terms, which is a contradiction to what we know about how integers work. And so, what I'd like to do today is to start off with an activity where I would like you all to work in, let's see, groups of 3, let's say. Groups of 2 to 3. Again, Steph are already eyeing each other. Where I would like you to determine, as part of our proof, see, we'll have to look back up your notes from last class. As part of our proof, what were kind of things that we assumed throughout our proof that are not any of Euclid's axioms or things that we've already proven? So what are some kind of our big assumptions that we made as part of our proof that somehow did not rely on any of Euclid's postulates? Because there were a few things that we kind of assumed throughout our proof that did that. So let's see. For today, I'll let you all sit where you are and group however you want. But talk to your neighbors and see what assumptions did we make because I want to write those out on the board so we can talk a little bit about them.
Hello. Like calculus 2 buddy. Together again. Sure. Come on in. You gonna sit here?
Yes.
Great. We're really gonna.
Sorry, you might want to talk to the neighbors.
It's gonna be easy to put back in. Oh, sure. Sure. All right. So now we have all the steps, we just gotta find out which one step is assumed. Yeah. We assume the rules of how yeah.
Interesting. Rules of arithmetic showing up.
Okay. Suppose it's a right triangle. That's a good point. That's crucial by. Oh, okay. We just have to go. So that is. So yeah. Well.
That X and Y have to be in.
So all we did was go through it and we
Oh, so you're just saying any
I
algebra
don't think that he would get unless we were assuming.
that A is upside down, it's automatic, right?
Yeah, you assume that. So it's the reduction thing, it's number in front that you got.
I didn't get your text. So I will send you over. I'm sorry about that. Just my phone is dead.
We need to specify one. And then here.
Oh, were you able to?
Where it's
I think it's just even odds.
where the two Y's or
Like x squared over y squared equals 2 means that.
Arithmetic.
Yeah.
I feel like algebra is arithmetic.
What goes into that? Oh yeah, because x equals 2y squared. Oh yeah, that's the definition of
Or I guess
I don't know, n equals 2 m.
doesn't algebra mean like?
Or no, n is even if there's an integer m such that n equals 2m. Yeah. So that's a definition that isn't in Euclid, so we can write that down, right?
It misses one or two for the first few chapters and it gets off to like, no, I don't
Ow!
here, we are assuming
Why?
we're saying that.
Unless I'm not.
Okay, let's come back together now, and I want you all to kind of I want to share as a class what you all found, kind of looking through our proof of what are some things that you found that we kind of assumed or used but never actually proved at all.
Pythagorean theorem.
That's probably the big one I had in mind. Yeah, Pythagorean theorem. That's a big one. Proved towards the end of book 1 of Euclid's Elements, like several dozen propositions in, relies on lots of different propositions. That ultimately can boil down to the postulates, but that's a big one where right away we assumed, oh, AC squared has to be AB squared plus BC squared, so that told us that that x over y quantity squared had to come out to 2. Any other assumptions you all found? Yeah?
That we can distribute an exponential among the numerator and denominator of a quotient.
So, in mind, but yeah, the arithmetic works is that PEMDAS works the way you want it to, I guess, would be a way to put that.
Well, just like how we can't use degrees and stuff like that, I don't know, I feel like this relied on integers that aren't technically geometric, and I wasn't sure if you could really do that.
Ooh, they relied, yeah, this is a theorem that was stated very geometrically, but the proof was very much, actually came out sort of a more number theory-esque proof, where we're looking at properties of the integers, primeness. So I guess the assumption you could maybe put is that we could use algebraic properties to talk about geometry.
Yeah, I said we assumed algebra and number theory, so.
We assumed algebra and number theory. I like that. That's a broad one. Yeah.
We assume that if the square of a number is even, then the number has to be even.
Yeah, that was a big part of our proof. We used that twice, I think. I'll say if x squared is even, then x is even. And for both x and y in our proof, we needed to use that. Jared?
Oh, I was gonna say we could prove that pretty quickly, but then I realized that was the point.
Oh yeah, I'm not saying none of these are things we can't prove, but they are things that we didn't prove.
Kind of going off algebra, but we assumed that we could substitute x with s. We could substitute x for another with another value that we come up with.
That we could substitute variables?
Yes.
Okay. We can substitute any others? I would say this last one, as well as maybe x over y quantity squared, would be things that Euclid would probably have assumed as part of his implicit rules of logic. Not anything he ever set out as a rule, but things that he would implicitly assume. Hey, yeah, that yours is interesting. Just kind of assumed in general we can use algebra and number theory to do geometry. And I think Euclid or even the Pythagoreans would argue that they're all interconnected and related. That there is no, I guess, explicitly written rule about when is it okay to use tools from one branch of math in another branch of math, so to speak. Pythagorean theorem is definitely a big one that relies on a lot of machinery that we just kind of used right at the start. And we didn't have Pythagorean theorem, our proof would never have taken off the ground. If x squared is even, then x is even. That was an important part. Here's one that I had. Any fraction can be written in lowest form, lowest terms. Unless you want to fold that into the umbrella of, we assumed algebra and number theory. But that was a key part of our proof. The fact that we could write x over y in lowest terms to begin with, because that was ultimately our contradiction. That even if we assume from the get-go that x over y is in lowest terms, we showed that x and y still had to have a factor of 2 caked into them. So, in essence, the reason why I wanted to do this activity is I wanted you all to start thinking about and see what are sort of our underlying assumptions that we're making as part of our proof writing. And ultimately, as much as possible, we'd like to be able to eliminate things from just being assumptions in this class and make them into either things that we can prove, or at least things, at the very least, things that we're aware that we're using without proving. Because in the study of geometry and math in general, as much as possible, you want to prove every result that you're using. or at least know that someone else has proven it along the way. Any questions or comments? Okay, let's see. Who do I want to pick on now? You want to be picked on? Sydney, I'll go with you. I want you to make an assertion that you know is actually false.
Plus 2 is 5.
Ah, okay. So Sydney's making the assertion that 2 plus 2 is 5. Okay? Okay. So you agree that 2 plus 2, you believe that 2 plus 2 is 5. So then you would very strong feelings. So then you would naturally agree that if we removed a 2 from each side, that would tell us that 2 is equal to 3. Then you would naturally agree that we could subtract 2 again from each side and find that 0 is equal to 1. Then you would naturally agree that we could multiply each side of this equation by anything we want, say some value n, and find that n has to be equal to 0 for any number n.
That made math a whole lot easier.
That would make math a whole lot easier. So then you would agree that 0 is the only number. So you would agree that that there is nothing in the universe because 0 is the only number. There is nothing. You agree that you do not exist.
Yes.
At some point I want you to say, sorry, Dr. Herzl, I guess there was a flaw.
Well, in that case, no. 2 plus 2 is not equal to 5.
Aha! So you don't agree that you think that you do exist. Therefore, 0 cannot be the only number. Therefore, your initial assumption must have been flawed.
Yes.
My goodness. What's this an example of? Any of you taken philosophy? Derek?
Reductio ad absurdum.
Reductio. Oh, that's the point of the activity, yes. I was trying to get at, it's the Socratic method.
Oh.
A student makes an assertion, and then the teacher basically plays devil's advocate and says, Sydney, you have made an assertion. I'm going to take that assertion and logic my way to an absurd statement. So Socrates was kind of famed for kind of using this method as a method of discourse, of a way of describing, of kind of finding and discussing logical statements. And so I'll just write this down, that the Socratic method is based on discourse. Where the student makes an assertion. Then the teacher, or whoever the teacher role is, Socrates perhaps, takes the assertion, and basically says, well, under the premise that this assertion is true, we can logic our way to an absurd statement. An absurd statement like, Sydney, you do not exist. You do not think, therefore, and you are not. I'm going to stop there. You do exist. You are a valued member of the But then the teacher takes the assertion and logics it out to an absurd statement. That's the Socratic method, famous as methods of discourse. And if you're on the debate team, Jared, you made an interesting observation a minute ago. What is another way to refer to the exercise, this method of logic that we just did.
Reductio ad absurdum.
Indeed. This is the exact same idea as reductio ad absurdum, proof by contradiction. This notion that that we assume the opposite of what we want to show. In other words, we assume something that we want to show is false, and show that by assuming it, we can logic our way to an absurd statement. And so ultimately, this proof technique, which is going to be one we rely on quite a bit over the course of the semester, which is why I wanted to go carefully through this proof last class. This proof technique of reductio ad absurdum is really just the Socratic method in disguise. Or maybe I should say the Socratic method is reductio ad absurdum in disguise. So just give a sense of sort of the historical underpinnings of how is this proof by contradiction technique used? How is it going to be important, not just in our modern day use of math, but also in kind of historical discourse? Is it really comes down to this Socratic method from Socrates. Any questions or comments about that? Okay, it may shock you to know that even to this day, there's people out there who don't like reductio ad absurdum. I know, shocking. They think that it doesn't, that logically it is flawed and doesn't make sense to assume that a false statement and show something contradictory occurs. They think that that is not a valid proof technique. There are a bunch of weirdos in the mathematical world doesn't like thinking about them or talking to them. But here's a thought, or here's a question. If you were to remove reductio ad absurdum from your acceptable proof techniques, what effect does that have on the math that you're allowed to do, the math that you're thinking about? Right?
It would be extremely difficult to disprove things.
It would be extremely difficult to disprove things. Yeah, it certainly would. I would also say that it has the net effect of, let's see, Sydney, did you? I would say that if you were to reject any rule of logic, and here I'm going to think about proof by contradiction, reductio ad absurdum as a rule of logic. If you were to reject that rule of logic, not only does that make proving things in the future more difficult, but it also means that any result like this one that's been proven by use of reductio ad absurdum in the past is no longer something that you can rely upon. Because it was proved using a technique you don't like, an invalid proof technique. And so the moral is if a rule of logic is rejected, then all results that flow from that, that rely on that rule of logic, can no longer be relied upon. And the way I want you to think about these rules of logic is like this. In a way, they're just like the postulates, the assumptions that you make, like between any 2 points there exists a unique line, and that the rules of logic, like reductio ad absurdum, form the building blocks that you use to make math. It's like if you have this beautiful mathematical castle, and you remove reductio ad absurdum pillar holding up the walls, part of the castle is going to come crashing down. It's going to come crumbling down. You took away one of the building blocks, one of the supports that you needed to build up your mathematics. And so the same would be true if we remove something like the parallel postulate. You don't like Euclid's postulate 5? You don't like the parallel postulate? well then a lot of geometry that relies on the parallel postulate comes crashing down to the ground. And that is why we're going to be spending so much of the semester seeing what's left of our mathematical castle after we remove the parallel postulate. What can we still say is true? And what new extensions can we add onto our castle of mathematics that doesn't rely on the parallel postulate and in fact can fly directly in the face of the parallel postulate? I mean, it's logically inconsistent with it. Jerry?
Yes. I was wondering about reductio ad absurdum, but it might be a tangent. Can't that be proved with more basic rules of logic, like non-contradiction and something else? Or stuff.
Yeah, of course, there's lots of kind of either equivalent ways of looking at, there's lots of sort of equivalent ways of looking at reductio ad absurdum, and just because you have a theorem like this where even if you reject reductio ad absurdum, that doesn't necessarily mean you couldn't prove these results some other way. That's why I say results that rely on that rule of logic can no longer be relied upon. It doesn't necessarily mean they're false. It just means if you want to use that as a result, well, now you need to find some other way to prove that. And so, before you can rely upon it as a result again. So just because you're removing a rule of logic from your lexicon does not mean, or from your toolkit, let's say, does not mean that suddenly all these results are false and all hope is lost from the universe. For instance, when we get into what's called neutral geometry in chapter 4 in the book, which is geometry where we assume basically all of Euclid's other stuff except for the parallel postulate, we're still going to see that some of the results that Euclid relied upon, that Euclid used the parallel postulate to prove, are still going to be true, but we're going to prove them using other ways. And then there will be some results relying on the parallel postulate that will no longer be true, and we'll see what's going to be true in its place. Are there questions or comments? All right, I've been teasing this for the last 2 weeks. What happens if we do non-Euclidean geometry? It's time to do some non-Euclidean geometry. So this is a cutoff point for Friday Swift code. By the way, no serious mathematician discounts reductio ad absurdum or proof by contradiction. Historically, there have been some, and there's some modern-day philosophers, I think, that don't like it. Exactly, we don't talk to them. Okay, so, how many of you have gone to Dr. Murphy's office and seen the poster on his office door?
42.
David Hilbert. They have our corner of David Murphy and Dave Gabler. So they have like a David Hilbert poster hanging up, kind of celebrate the fact that like David Hilbert's probably the most famous mathematician whose name is David. The reason why I bring this up is we're going to be talking about the works of David Hilbert, who was a German mathematician in the late 19th and early 20th century. Let's see, there's minutes. Let's see, he lived from 1862 to 1843. And David Hilbert is commonly said to be the last mathematician who did math in basically everything. Algebra. He has a bunch of results in algebra, in geometry, in topology, in analysis, in dynamical systems, in mathematical modeling. If you can name a branch of math, David Hilbert dipped his fingers into it at some point in his career. So famous. He's the one who came up with these like Hilbert's unsolved problems that like he's at the dawn in 1900, which he said were like these are the biggest questions known to math today, which shaped for pretty much the whole 20th century what were the problems that mathematicians tended to work on. In other words, he's a big deal. Apparently I just left my thought at famous. I'm gonna leave it there. You don't need to know much about Hilbert the man for this, but what we're gonna do is Hilbert decided he wanted to redevelop Euclid's axiomatic system geometrically. Let's write that down. Redeveloped an axiomatic system for geometry that was designed to sort of fix some of the things that he thought were flaws in Euclid's work. Things like, in proposition 1, how do we know these two circles have to have a point of intersection? And so, right, for the next several weeks, in fact, I'm going to spend quite a while working through Euclid's axioms in the rest of Chapter 2 and Chapter 3 in our book. We're going to be looking at the axiomatic system that Hilbert developed, which is going to behave a little bit differently than Euclid's axioms. For one, there's going to be more of them, but it's also going to be a bit more precise in some ways than Euclid's axioms. And notably missing is going to be the parallel postulate. So to start up, here's how Hilbert's system works. Hilbert has some mathematical terms that he very purposely does not give a definition for. And for instance geometry, which is kind of going to look at Hilbert's first three axioms, the instance axioms, the three terms which we're very purposely not going to define are points, lines, and the idea of incidence. What it means for a point P to be incident to a line L, or more colloquially, to lie on a line L. You might have some heavy intuition as to what you think it means for something to be a point, for something to be a line, and what it means for point P to either lie on line L or to not lie on line L. But we're very purposely not going to define these terms. And what we're going to do instead is we're going to look at Hilbert's three incidence axioms, which are just like Euclid's axioms, they're going to be, or just like Euclid's postulates, they're going to be these mathematical statements that we're going to assume but not prove. And then we're going to look at, once we've looked at what do the axioms say, we're going to look at how can we define points, lines, and the idea of incidence in several different ways that allow us to come up with different systems of geometry that all rely on the same axioms but use different definitions. And that'll get us the idea of our first non-Euclidean models of geometry later in the packet. So for now, you can use your intuition as to what you think points and lines mean. In fact, I'm going to draw some pictures that use our kind of what you probably think they mean. But we're very specifically not going to define these terms quite yet. So first axiom, probably one that might look familiar to you. I'm going to write IA1, IA being incidence axiom, because we're going to have to distinguish these later on from betweenness axioms, congruence axioms, continuity axioms, and I don't feel like writing out instance axiom each time. First instance axiom. For every point P, and every point Q not equal to P, there exists a unique line L incident with P and Q. Where have we seen this result before?
Sounds like the modern definition for Euclid's Euclid's axiom one.
Yeah, this is just Euclid's first axiom. Written out maybe in a slightly different form, using different language, using the more modern version where we're not going to forget to explicitly write out the word unique. But this is really just modern Euclid first postulate. You give me a P, you give me a Q, there's going to be a unique line that goes between them. So far, Hilbert really liked this axiom of Euclid, so he's going to keep it around. What about, it's going to be the only one that Hilbert keeps, at least in the same form, at least in the same basic format as what Euclid had. 2 points to find a unique line. That's something that Hilbert thought, yeah, that's pretty intuitive based on what he thought lines and points should be. These things which we're very specifically not defining. But whatever points, lines, and instants mean, here is a result that connects those three terms. The second one is going to say for every line L, there exists at least 2 points, 2 distinct points instant of L. So if I were to draw a line, I should be able to find at least 2 distinct points on that line. I don't know. Hey, this looks like a point on the line. Oh, I found another one over here. If you have a line, there should be at least 2 points on that line. Is that one that you all feel like fits with your intuitive understanding of lines? You might be thinking, Dr. Herzl, don't lines have infinitely many points? Maybe. At least 2 could mean infinitely many. But we're going to be considering some cases where what if lines only have a finite number of points? At least 2, but not necessarily more than that. And finally, instance axiom 3, going to be a big one that you might think, Dr. Herzl. Is there exist 3 distinct points with the property that no line is incident with all of them. There exist 3 distinct points with the property no line is incident to all of them. So I should be able to find 3 points somewhere in the universe. Let's say here's one of them, P. Here's another one, Q. And here's another one, R. And there's no line that happens to pass through all 3 of these points. Now the first axiom, I can find a line that goes through P and Q. I can find a line that goes through Q and R. I can find a line that goes through P and R. P and R. But somewhere in the universe, there exist 3 non-collinear points. 3 points that do not all lie on the same line. And to start with, that's it. Those are our only things in instance geometry that we're going to be allowed to assume. Assuming things like parallel lines exist. No, we're not assuming that. Assuming things like all right angles are congruent. You know, what is this word congruent you speak of? What are these right angles you speak of? For that matter, what's an angle? We're not assuming anything. We just have 3 undefined terms, points, lines, and a point is incident to a line. And these 3 results that we're going to be relying upon for the next week or so of this class. Any questions or comments so far? I hope you all agree that the standard definitions of points and lines and points being on lines that you're used to thinking about all satisfy these three axioms. But for now, the rest of your intuition, I want you to do as much as possible, throw it out the window. Don't make any assumptions. Save it for other math classes. Other math. So, what can we do with this? Well, first of all, now that we have these terms, we can define a few more terms relating to points, lines, and incidents. And here are some terms that we are going to give definitions for, because they're going to be handy to have to work with. First of all, collinear. Three or more points are collinear if they're existing a line that goes between all of them. 3 plus points A, B, and C are collinear if there exists a line incident with all of these points. So in other words, a line. Are these 3 points collinear? You know, we haven't defined what it means, what a line is.
Okay.
You know, here's a line through. Good.
But wouldn't that invalidate the third?
What? The third postulate, or the third instance axiom just says there's 3 points somewhere in space. I don't know, maybe here they are. Such that no line goes through all 3 of those points. That doesn't necessarily mean there can't be 3 other points in space that are collinear. Just because some points you can't have a line through all of them doesn't mean you can't have other sets of 3 or 4 or 5 or infinitely many points for which a line does pass. These are, I'm glad you said that, because these are the sorts of things we're going to be confronting in this class. Intuition about what you think things mean and what they actually mean. But yes, with our normal understanding, Elaine, of what collinearity means and what points, lines, and incidents means, these are not collinear, whereas these 3 points would be collinear with our usual understanding. In case you haven't figured it out yet, this class is going to have a lot of trick questions. Similarly, we can define concurrence of lines, where 3 plus lines are concurrent if there exists a point that is incident with all of the lines. So 3 plus lines are concurrent if there exists a point in common with all of them. Brianna. Are these 3 lines concurrent?
Since we haven't defined a line yet, sure.
All right. Let's make this a little bit nicer. Purposely just trying to confuse you. Are these 3 lines concurrent? How do you know?
They share a common point.
How do you know? What's the point?
True.
No. I mean, it looks like I don't know, it looks like there's a bunch of pieces of chalk that are all meeting up there. That doesn't mean there's a point there. Brianna, are these three lines all concurrent?
Yes.
Yeah, now they're concurrent because there's a point there which they all meet up. I know some of you are probably thinking right now, all right, Dr. Herzl, enough of the cheap shots and questions. But but I do these 20% for my own amusement, 80% to bragging the point that points and lines are not going to be what you expect going forward. And finally, two lines L and M are parallel if no point is incident to both of them. And I could make this into another trick question, but I won't. There we go. Two lines which do not appear to have any points in common, according to our visual intuition of what we think a point lying on a line means. But Dr. Herzl, why can't this point be on this line and that line? Because we haven't defined what it means for a point to be on the line. Maybe it just means they exist in the same two-dimensional space. But according to what our intuition tells us, these would be parallel lines in that they don't have any points in common. Same definition of parallel that you're used to. We just might be using it in different ways.
That would break the third incidence axiom.
What?
If you're doing a 2D geometry and a point is on a line, if it's on the same two-dimensional space, then every point is on every line, and then there's no point that's not on a line, right?
But how do you know? How do you know? What if we take this point, and pretend I'm going to draw a point on your nose? That point.
Yes.
Those would be 3 points that do not all exist in the same space, and no line passes between them.
Oh, you can have literally different two-dimensional spaces.
We're not going to in this class. We're always going to be assuming we're working in the same two-dimensional space, but theoretically, sure, why not?
Sure.
Question. You notice both these definitions for collinear and concurrent require 3 or more things. We need 3 or more points to talk about collinearity and 3 or more lines to talk about concurrence. Why do you think that's necessary? Why do we need to have 3 points, for instance, to talk about collinearity? Elaine?
Because if it was just 2, then by the first axiom, there's going to be a line through them. I mean, that's by the definition.
Yeah, exactly. Collinearity, we generally want to refer to 3 or more points because if you have 1 point, then that just doesn't really make any sense. And 2 points are always going to be collinear by incidence axiom 1. Between any 2 points, there has to exist a line. So you need to have at least 3 points that you're working with in order to be able to ask the question of, are these points collinear or not, be an interesting question. Something that could be true or something that could be false. Not something that's either always true or something that's meaningless. So collinearity requires 3 points for that. How about concurrence? Would it make sense to talk about 2 lines being concurrent?
Would you say that if it was only 2 lines, it would be incident, and so you kind of like an overlapping definition?
We're not going to use theoretically, yes. Practically speaking, with incident, we don't usually talk about 2 lines being incident. We're usually going to refer to a point being incident to a line. But we're not going to use the term incident to refer to 2 lines intersecting with each other.
Any 2 lines are going to be concurrent unless they're parallel. So it's kind of like
Yeah. It's more to distinguish.
of the parallel definition.
Yeah. It's really 3 plus here is really to just distinguish concurrent from non-parallel. Because if you allow for 2 lines, 2 lines intersecting, according to what our intuition of what the word intersecting might mean. is really just the same as saying they're non-parallel. So we could have concurrent or collinear refer to just having 2 points or 2 lines or 2 points respectively, but we have other ways to kind of refer to those things, such as there are 2 points that exist, so they have to have a line between them, or just for 2 lines that happen to intersect, they're non-parallel. I'm going to do the best I can throughout to try and avoid using words like intersecting, which we're not going to define. If I do, you can point it out and say, Dr. Herzl used a bad word, and I'll apologize and put money in the swear jar or something. And with that, we'll call it quits for today. So when we come back on Friday, we're going to start proving propositions from the 3 incidence axioms, and then hopefully in the second half of class we'll have time to start giving definitions to points and lines and incidents that you might not be used to working with. Hope you all have a good rest of your day. I'll see you all on Friday.